All right, so standard deviation is kind of the foundation or the basics that's necessary for us to do the rest of this course. Okay, almost everything that we do beyond this is going to involve standard deviation. Okay, now what we're doing by hand here is going to be something that we don't do on every problem. Okay, so we're not going to collect all the data, but they might give us a scenario where they say, we've already done the data collection, here's what the standard deviation is, now you've got to do this other work. Maybe we're doing like hypothesis testing or something like that. And we need to understand what the standard deviation is in order to do that. Okay, and I also think we need an appreciation for what the formula is actually doing. So that's why we're going through this by hand. Eventually, I'll give you some tools with Excel, Desmos, GeoGebra that will allow you to find the standard deviation quicker. But right now, I want to go through the actual process. I think you gain an appreciation for it. You understand what the standard deviation really is. So that's kind of what we were talking about in the last couple of videos. So again, standard deviation, I'm going to go back up. I know I talked about this in the videos, but you've got these formulas. And my hope is that we're not memorizing those formulas, at least collectively. I think you should probably only learn one of them. Okay. I would learn variance. Okay. I would learn this first one up top. And obviously that's for a sample. And the only thing that's difference between the variance for a sample and the variance for a population is what we divide by. Okay. In a sample, we divide by n minus 1. In a population, we divide by the total number of the population. Okay. And what that does is if we divide this one by n, what happens is our estimation, or I don't want to say estimation, our variance is too small. Okay. So what we do is we divide by a lesser value of 1, and that will give me a better variance, and it will be a better estimation of the population. Does that make sense? Now, I'm not going to get into it's a lot higher level of like statistical analysis that allows us to come to that conjecture that we divide by n minus 1 instead of n. But that represents to how many, n is obviously how many things are in your sample, and then minus 1. And then here n would be, obviously we don't have a sample of the population, but still the total in that group of data that you're using. Does that make sense? X bar is the mean for a sample. Mu is the mean for the population. Okay? But we treat them the same. They're both arithmetic means. So if I can remember this one, then hopefully it allows me to also know the variance for the population. And then if I square root things, those gives me the standard deviation. That's what we're really looking for here. The standard deviation is the idea, if we were to look at like data points, and I mentioned this in one of my videos as well. If we're talking about like weights of students, okay, and we did it in kilograms, that number right there minus your mean would be a kilogram minus a kilogram. And that would give me a unit of kilograms, right? Does that make sense? Okay, so maybe it's 100 kilograms minus the mean of 98 kilograms. So then I would get 2 kilograms here, okay? But this is telling me, so that's called a deviation, okay? To deviate from something means to move away from it, right?
Right.
Okay. Some of us deviated from the tasks that I asked you to do in class the other day, right? And watched ESPN or Hulu or, yeah, okay. So then when so our deviations, some of them could be positive, some could be negative. And if some are positive, some are negative, they're going to cancel each other out. And that's not what we want. So what we do is we end up squaring that. And that will generate positive, essentially deviations, okay? The same thing happens if you ever like analyze, like you guys remember lines of regression and least squares and that kind of stuff? You ever do that in science or Algebra 2? Okay, same thing happens there. We want to make the differences essentially all positive. Because when we talk about deviations, we're talking about distance away from something. Distance away will be positive. So this gives me now 4 kilograms squared. Have you ever seen the unit of kilograms squared somewhere? It doesn't make sense, right? Okay. Now, if we were talking about like inches or feet, you could end up getting inches squared or feet squared, and those are units that make sense to us. But in comparison back to the original data, if the original data was like height and it was in inches, and then your deviation then would be in inches squared, there's still different units that aren't comparable, right? Does that make sense? So kilograms squared isn't even a unit that we would ever talk about. And the same reason, though, it doesn't compare back to kilograms. So it's a meaningless value because of the units not having any real true meaning. So to fix that, we take the square root, and we take the square root, it takes the square root of the units, it puts it back into kilograms. Does that make sense? So the standard deviation then, the standard deviation is going to be in the same units of the data that we collected. Now, what does the standard deviation allow us to do? The standard deviation allows you to essentially take and we'll get to this at the end of the period today. It allows you to take an individual data point. So let's say that we're talking about like our heights in this classroom, okay? And we take Lucas's height, okay? Lucas, probably tallest person in here, right?
Right.
And what we can do, so if we take the average of everybody's height in here, and that becomes our mean, okay, that's our population mean, we can then take Lucas's, okay, take his individual height, and because we now know the standard deviation, we can determine, is his height unusual, okay? Is it outside of what we should expect most of our data in this room to exist in? That make sense? Okay. So it allows us to compare particular data values to the entire population, okay, or to the entire sample. In addition to that, it allows us to eventually compare from two populations. And we'll talk about things called the z-scores, which is at the end of today. So that's what the last couple of videos discussed, is how we deal with standard deviations, okay? I want to scroll down here. We're going to talk about a grouped frequency distribution. I mentioned this when we talked about the averages. If you guys remember back to, let's see here, centers of data, we did this example here where I didn't necessarily, if I sold 15 and 19 papers on that day or during this week, and it happened twice, or I guess it was a 10-day period or something like that. I had to go look at the scenario, but I think it was a 10-day period. How many papers we sold? Yeah, it was a 10-day period. And 15 and 19 papers happened twice. 20 to 24 happened 7 times. But I didn't know, maybe 15, maybe these two represent for 15. And then it was 0 for 16, 0 for 17, 0 for 18, 0 for 19, right? Or maybe those two actually represented 18, and it was 0 for the others. Or maybe one was 16 and one was 17. Does that kind of make sense? I can't, because I don't know what the raw data was, I can't guarantee or verify what that frequency represented. So what we do is we estimate it, and the best estimate for us would be the midpoint here. Does that make sense? Okay. Same thing here with these 7. Okay. They all could have been 20. They all could have been 21, 22, 23, or 24. Okay. But maybe 1 was 20. Maybe 2 were 22. Maybe 3 were 24, and 1 was 23. Okay. I don't know. But if we just make them all the midpoint, that's a better estimation. Does that make sense? So when we talk about group frequency distribution, we don't have the raw data. That's the approach that we're going to use, is the midpoints. So same thing happens when we talk about standard deviation. Okay, so in this particular, and I'm going to actually, I think the best thing here is to actually develop this using Excel. Okay, just because of the calculations that have to be done. You can do it by hand. You can do it with TIA3 or whatever, and you can, pound out those numbers, but that's a pain in the butt to type in a calculation, write it down, type in another calculation, write it down, type in another calculation, write it down, and then sum all those. That's a pain in the butt. If we've got Excel that can help with that, let's use it. Okay, so I'm going to first talk about, if I'm trying to find the mean, I'm going to try to find standard deviation, but in doing that, we need the mean. Okay, if I look at my intervals here for my class, our midpoint exists at the halfway point, right? Okay, so how do I find the midpoint between 20 and 29.9? Do you remember how to do that? Add and divide by 2. So I get that for the interval of, or the midpoint of that first interval. So now here's my next question, because I could then do the same thing, write another formula for this next one, okay? But what is the class width of my intervals here? What's the class width between, remember the class width is,
10.
It's 10, right?
Yeah.
So that means that no matter where inside that interval, if I add 10, so if I'm somewhere inside this interval and I add 10 to it, it gets me to the same spot inside the next interval. Does that make sense? So if I'm residing at the midpoint in this interval and I add 10 to it, don't I get to the midpoint in this next interval? That makes sense? So what I'm going to do is I'm going to say, I'm going to hit equals. I'm going to take this last number, which is A2. I'm going to add 10 to it. What did I just added 1. Add 10. That gives me that, right? And now I can click and drag that all the way down as far as I need to, and I don't need this last one. Does that make sense? Okay. Now there's another way of doing it. Just kind of show this real quick. We know if the class interval or class width is 10, then I can actually just, instead of making a formula here, can I just type in 34.995? And then the next one, could I just type in 44.995? And I could keep doing that, which would be obviously a lot less efficient than creating a formula. But if I've developed the pattern between two cells, if I highlight those two cells, you see this little box down here in the right-hand corner? It's very small. But when I put my cursor on it, my cursor changes from this kind of block crosshair to the thin crosshair. When I do that, basically what it's saying, whatever the pattern is right there, capture that pattern, and then replicate that pattern as much as we need to. And I messed it up. And it's because I had a formula in there, so it was messing with the formula. So if I got that pattern, did those two things by hand, grab this one, pull it down, and you can see then that it will create that pattern and continue that pattern all the way through. Is that okay with everybody? Okay. I'm going to list or label this list as midpoints. Okay. Over here we've got our frequencies. So I'm just going to type those in real quick. Okay. So if we go back to finding the mean, and this is what we talked about in section 2.5, I think it was. It's the sum of the frequencies times the midpoint. Okay, so if I want F times M here, it's going to be equal to, this is the frequency cell, and then multiply it times my midpoint cell, right? Does that make sense? And I get 1,249.75. Okay, so I had 50 data points that fell inside this interval. Okay, some of them were 20, some of them were 29.99, and some of them were in between there, right? We're going to make the argument that they all occurred at the midpoint. Okay, and if you think about it that way, then those values that occurred above the midpoint and the values that occurred below the midpoint, some of those would have canceled each other out, right? Does that kind of make sense? All right, so it's a good estimation to say that they all occur at the midpoint. So now that I've got that, I'm just going to click and drag that box straight down. And what I like to do to make sure that this all copied correctly is I just click on one, double click on it, and it will highlight the boxes and it will show the formula that's being used with those boxes. So that's what I want. I wanted this frequency times that midpoint, and it should give me what should be in that box. Okay, click on this one down here, that frequency times that midpoint. So I know what's in those boxes is what I wanted. Does that make sense? Okay. Now I'm gonna actually find my mean. So I'll write mean down here equals. Now in order to find my mean, I need to know the sum of my frequencies, right? I need to know that right there. Okay. So that would be the sum of those right there. Does that make sense? So just hit equal sum of B2 to B9. And that will then give me 248. That is my sum of my frequencies. I also need the sum of my frequency times my midpoints, because that's my numerator, correct? So I'm going to do that one. I'll hit equal sum, and then we're going to go C2 to C9. And I'm just going to put sum here, just to remind myself that that's the sum of the frequencies, and that's the sum of frequency times midpoint. So then my mean would be, because that's my numerator, right? That's this quantity right there. And 248 is my denominator. So I'm going to type in equals, and I'll capture C10 and divide it by B10, which I'm zoomed in. So sometimes when it zooms in, it won't let me capture that box or the cell above where I'm currently at. So B10 that way. And there is my mean. Is it okay? Okay. So that's the first part. And the reason we need our mean is because then when we talk about the standard deviation for a group frequency, there's our formula. Okay? And on the test, guys, I'm not going to ask you to memorize these formulas. I'll give you the formulas on the test. Okay? But what that says is we're going to take the square root of the sum of f, which f represents the frequency, right? Times m, which represents your midpoint, minus x bar, which is your mean, that quantity squared. Okay, and then we'll divide by n minus 1. So, what we essentially need to do in this table here, I kind of set this table up for you in your notes, is exactly what I'm doing on Excel. Okay? X bar is my mean. Okay? So that was equal to B11. So
please pardon the interruption. For the volleyball players, they should have or should be leaving at this time. There was a list on your absence sheet, so they are able to leave at this time. Thank you.
good luck.
I said it first.
All right, so in my table, I'm just going to put that X bar value and I just drag it straight down. Okay. This next column is going to be our mean and our mean is X bar and our midpoint is M, right? Okay. So we go midpoint minus X bar. Okay. Obviously, writing my headers here would be nice if I could use the actual math notation, but I can't. So my midpoint, I'm going to go capture that, which is this number here, and then minus X bar, which is that number there. Okay. So that is my deviation. That's what we were talking about in the standard deviation formula. Okay. I'm just going to drag that straight down. I don't want it there, and I didn't want it there because this was my row for my sums. So let me just color that so I don't add anything into it. All right, so the idea is if I just left these this way, that number right there and that cell and that one there pretty much negate each other, don't they? Okay, and that would be a problem. That's why we don't, when we take our standard deviations, we don't want to have that situation occurring. So that's why we take in our next column the midpoint minus X bar and we square that. So all it is taking this cell here, or this quantity, and squaring it. So I'm just going to type in equals E2 and we'll square it. And I'll drag that down. Now you see that everything is positive, right? Okay, so there's no when we add those up, there's no cancellation. Okay. So now going to our formula, let's see if we've got everything we need here for our formula. Our formula was frequency times midpoint minus x bar squared, okay? I don't have all of that yet. I've got the individual parts, but I don't have it all yet. So we need to take and create another column that says frequency times midpoint minus x bar squared. So frequency was what we were finding in B2. And we're going to multiply that then by the midpoint minus x bar squared, which would be F2. Hit enter. And then once I have that, I'm going to drag it straight down and do it for every one of those classes. Okay? So here's the thing, guys. If we were doing this by hand, you had a TI-83, A4, TI-30 in your hand, you would have to do all those calculations and whatever precision we were asking for, so how many decimal places we were interested in, you would have to write all these things down, all these numbers down. You have to calculate them first on your calculator and then write them down. Would you want to do that? No. And I'm not going to make you do that. If I ask you to find standard deviation on a test or a quiz, and I want you to do it by hand, I'm not going to be using numbers like this. I'll make things work out nice. Does that make sense? So we're not worried about, I'm more worried about the process and not so much your precision. So I'll keep the numbers like small and make sure they work out the whole numbers, or tenths place or hundredths place, make it pretty easy to do by hand. But this is a much more efficient procedure. So now we can sum these. Okay, so this would be my numerator. So I'm going to sum these. So I'll hit equal sum of that list right there. It should actually go to G9. And I get that quantity right there. Is that okay? Okay. So right there, that 122 number is the sum of your frequencies times your deviations squared. Okay. I need to divide that by n minus 1. And then we'll take the square root. So n was our total number of data points. So it's 248, right? So when we find, I'm going to come up here, right, variance equals, and I'll take this number, and I'll divide it by 248 minus 1. So I'm just going to type that in, 247. That didn't work. G10 minus, or divided by 247. My keyboard is stupid. My computer, every once in a while, will turn all, like no matter what I'm doing, I'll be typing and it'll turn all my keys into hotkeys. I have no idea why it does that. 247.
What's a hotkey?
So like if I hit like F right now, it'll like go try to find something, like a control, like it holds the control key down automatically. And sometimes if I hit Alt Control P, it fixes it, but that's stupid. All right, so equals that divided by 247 then. And there's my variance. Okay. I want my standard deviation, which is just the what of my variance? Square root. So I'm going to hit equals square root, SQRT, of that number right there. And I get my standard deviation. Okay. So what this means, what's standard deviation mean to us? Okay. It's a way of determining how far away my data points are from the mean. Okay. The smaller that number, the more concentrated my values are on the mean. Does that make sense? Okay, so if we were to take a, let's see if I can find a quick picture. Something like this. Okay, so this is it's called a dot plot. Okay, if I was take so these are representing my data points, right? Does that make sense? Okay, let's say this column here was like my mean. If I've got a small standard deviation, all my little x's are going to be really close to that. Does that make sense? If my standard deviation, the bigger my standard deviation gets, the more spread out these things are. So this one here is going to have, if I were to actually do a standard deviation for this data here, that's going to be a smaller standard deviation than this one because this one has data that's more spread. Does that make sense? Okay. So a spread of 22, pretty large standard deviation. But what's even better is that it allows me to say, okay, if I know a particular data point out of there, I can actually compare it to the mean and get some analysis out of that. All right. One thing that we talk about, now we don't know anything about this distribution. If we go back to the story problem here that I've given you, it says find the mean, find the variance, find standard deviation. That's all I'm asking for. But it says find the mean and standard deviation of the income of people purchasing superannuation plans. Okay, whatever that is. Now, I don't know anything about that distribution. I don't know the skewness of it. Okay, so remember going back to this idea here. 2, 6. Okay. This is the type of data distribution that we would prefer. And this is the type of data distribution that a bulk of this course is about. Okay. Looking at what we call a symmetric distribution. And this one here is what we call a unimodal symmetric distribution. And when that happens, it's either normal or near normal in regards to its distribution. Okay, that's just a word we use. Which basically tells us that this is you guys have heard the bell-shaped curve before, right? Okay, that's a bell curve. Okay. These are skewed to the right, and these are skewed to the left. Okay. I don't know the data that we just collected, which one of these distributions that our data should model. Okay. There are techniques of sampling that will guarantee something like this, like simple random sampling will guarantee if we have a population, we make a sample big enough, it will guarantee that we get something that is symmetrical and unimodal. Okay. If this happens, we can make some analysis on very detailed analysis on our standard deviation in our data. If these other two distributions happen, or distributions that are maybe even more skewed, or maybe bimodal, or something like that, maybe even uniform, we can still make some analyses. They're just not as focused as what they would be if we were talking about a normal distribution. Okay, so that introduces what we call Chebyshev's theorem. I think Chebyshev was Russian. Okay. Says Chebyshev's theorem says the following list gives a few facts that provide a little more insight into what the standard deviation tells us about our distribution. Okay. And the formula for Chebyshev's it's actually a pretty simple formula that generates these facts here. It's 1 minus 1 over k squared, where k is an element of your natural numbers. So that means k is either 1, 2, 3, 4, 5, so forth. Okay. And what we usually do with Chebyshev's is we stay with k being like 2 and 3, and you see there's also a 4.5 in that third bullet. But what it says here, if k is 2, okay, if k is 2, it gives me 1 minus 1/4, which is 3/4, right? And that then is 75%, correct? Okay. The k represents the number of standard deviations from the mean. Okay. So when we have two standard deviations, and I know nothing about my distribution, okay, it is telling me, Chebyshev's theorem tells me at least, so we're setting a floor here, or the bare minimum, at least 75% of our data points will fall within two standard deviations of the mean. Okay, so what I want to do, I'm going to go back up to the previous problem. If this is our standard deviation, okay, I'm going to take my mean minus 2 standard deviations, and I'm going to take over here, I'm going to do mean plus 2 times my standard deviations, and see what that gives us. So our mean was this number here. What is that? B11. So I'm going to go equals B11 plus 2 times that number right there. Oh, I wanted minus. Sorry. I'm just going to copy this real quick so I can do it in the next one. So that gives me that number right there. Okay. Now I'm going to copy that and put it in this cell, but what do I want to do? I want to add 2 standard deviations, right? So think about what we're doing. We're just basically taking, so that mean was 55, right? 55-ish. This is saying subtract this number from it twice. So it gives me down to 11, right? This is saying, okay, take that 55 and add this number to it twice. And it gets me to that number there, right? Okay. So right now, what we've got is a range of values, a range of data values, that if we knew what each of these 248 data points actually were, if we had the raw data, what Chevy Chevs is saying is that 75% of those, so 248 times 0.75, 186. It's saying at least 186 of our data values will fall between those two numbers. Does that make sense? Okay. Chevy Chev's theorem guarantees that. Okay. Now, it then says if we want to go 3 standard deviations. Okay, 3 standard deviations. So all I've got to do is change that number to a 3. And this number to a 3. Oh. 3. So now I get a different range. And what that says is that 89% of our data will fall between those. So of my 248 data points, 220 of them, at least 220 of them, are going to fall in between that range. Is that okay? All right. Now, why is that important for us? If you guys ever read a study or heard a study of somebody saying that they'll come out with a poll that comes out like with the elections or whatever, they will say at the bottom, usually in fine print, that they're 95% confident that this was true, or they're 99.7% confident that it's true. Okay, those are called confidence intervals, and those confidence intervals have a foundation in understanding these distances of standard deviations away from the mean. Okay, and we'll better identify what that's called here in a moment. But we can do the same thing with 4.5. So 4.5, if that is the K value that I use, so it means 4.5 standard deviations above the mean and 4.5 standard deviations below the mean, then that will encompass at least 95% of our data. Okay, so Chevy-Chev's theorem is when we don't know anything about our distribution. Okay, we don't know anything about whether it's normal, skewed left, skewed right, uniform, bimodal, unimodal, whatever. We don't know. Okay, so we use Chevy-Chevs and that gives us that information. One of the key or main distributions we like to talk about is the bell-shaped or normal distribution, or even things that we can say are nearly normal. And we talked about symmetric, meaning that the mean, median, and mode are all the same value. Okay, we can have, there's all kinds of distributions that we'll talk about in this class. We'll talk about chi-square distribution, we'll talk about Poisson distributions. This is just one of them. And this is the one that we like to deal with the most because it has a great deal of probability kind of benefits of it, okay, or probability results that are very nice for us. If we have a bell-shaped or symmetric distribution, okay, we can use what we call the empirical rule. And the empirical rule just allows us to narrow those percentages that Chevy-Chevs was giving down to a little bit more precision, okay? If we know it's bell-shaped, okay, or normal, we can say that approximately 68% falls within 1 standard deviation of the mean. 95% within 2 standard deviations of the mean, and then it's actually 99.7% falls within 3 standard deviations of the mean. Okay, and these are the 68, and then we say 2 standard deviations. It's actually like 1.97 standard deviations or something like that, but we just estimate it back to 2 or round it to 2. Does that make sense? Okay. So what does that help us do? Let's say this here. If we've got, I'm just going to give you an image of a normal distribution real quick. All right, so if that's my normal distribution or my bell curve, and I've got my mean right here, okay, whether it's x bar or mu, okay, if I add to it 1 standard deviation, so plus 1 standard deviation, it's going to give me the there. If I subtract 1 standard deviation, it's going to give me the there, right? So what that tells me is that, what the empirical rule tells me is that 68% of my data is going to fall in that green region. Is that okay? Okay. If I go 2 standard deviations, it's going to take me out to here. Okay, and I'll highlight that blue. That means 95% of my data falls within the blue. Okay. Now, if I have a data point that exists beyond that blue region, so I find a data point, let's say we're going back to like our heights, and we find out that our heights are normally distributed, okay, and let's say Lucas's height was all the way out here, okay, that's beyond 2 standard deviations, right? So because it's beyond 2 standard deviations, we say that that height is unusual for the rest of the data. Okay? Does that make sense, everybody?
Yeah.
Okay. Let's see here. Something that allows, instead of having to look at the picture, something that allows us to determine unusual values as well is what we refer to as z-scores. And we will talk about z-scores tomorrow. Last class got through them, but at least one example, but no new homework. Like I said, we'll pick up with z-scores tomorrow. We'll talk a little bit more about this stuff on Wednesday, the first half of class, and then your vocabulary, the second portion. Cool? Cool. All right.